Let's take our time today to explore a few problems, specifically dealing with the change of base and conversion to the truth table. That's Boolean to a truth table and logic gate to a truth table. For our change of base example, let's take the number 3 25s, 2 5s, and 4, which is another way of saying the number 3, 2, 4 in base 5, and convert that to decimal. In base 5, you'll recall that we have 5 symbols. Let them be 0, 1, 2, 3, and 4. Again, there's 5 symbols in base 5. And there are places. For base 5, those places are 5 to the 0, 5 to the first power, 5 to the second power, 5 to the third power. We can continue on as much as we like in that direction. We could also go in the opposite direction. So 5 to the negative 1, 5 to the negative 2, and again, as far as we wanted to go. For this particular problem, this is all we need. We need the 1's place, the 5's place, and the 25's place. To convert to decimal, I would recommend you write the number in expanded form. In this case, this is the 1's, this is the 5's, and this is the 25's. So we can write that as 3 by 5 squared. So we have 3 25's plus 2 by 5 plus 4 1's. Any number raised to the 0 power, of course, is 1. We can continue on. This becomes 75 plus 10 plus 4, and I believe all of that adds together to 89. So we finished the problem by saying 324 base 5 is equal to 89 base 10. While this number is fresh in our minds, let's go the other way. Let's take the number 89 base 10 and convert it to base 5. From our previous discussions, we would say there's two ways to do this. There's a subtraction method, and there is a division method. We'll work both of those now, just so we can see them side by side. For the subtraction method, start with the places. So 5 to the 0, 5 to the 1, 5 squared. Again, those are the 25's, the 5's, and the 1's. Next, we take the original number, in this case 89. We write it here. Then we ask ourselves, how many times does 25 go into 89? The answer is 3 times. So 5 times 3 is 75, with a remainder of 14. How many times does 5 go into 14? The answer is 2. So that's 10, with a remainder of 4. And we can just move that number here. So when we're done, we would say that 89 base 10 is 3, 2, 4 base 5, which should be what we calculated here. As far as division is concerned, we start with our number, again 89, and we say 89 divided by 5 is equal to 17 remainder 4. We write the 17 here and the remainder here. Now, 17 divided by 5 is 3 with a remainder of 2. 3 divided by 5 is 0 with a remainder of 3. If you look, you can see the number is right here, with the understanding that we start from the bottom and work our way up. So once again, the number 89 base 10 is equal to 324 base 5. For good measure, let's work another example. This time we'll take the number 64801 base 10, and we'll push that to hexadecimal. You remember that hexadecimal is base 16. Using the subtraction method, we start by recording our places. 16 to the 0, 16 to the first power, 16 to the second power, 16 to the third power, and 16 to the fourth power. That's the 1s, the 16s, the 256s, the 4096s, and the 6553 Next, we take our original number and we move it down here, so 64801. How many times will the number 65536 go into that number? The answer is 0. It doesn't. How many times does 4096 go into that number? 15 times. So 4096 times 15 is 61440. We perform the subtraction, leaving us with 3361. How many times does 256 go into that number? The answer is 13. So 13 times 256 is 3328. We perform the subtraction once again, which leaves us with 33. How many times will 16 go into 33? The answer is 2. We record that as 32. Remainder 1, so we'll place the 1 here. This is a good time to go find that 3x5 note card. The note card where you put all of your number conversions on. You should have columns for binary, hexadecimal, and decimal. And what you'll find is that the number 15 in decimal is represented by the symbol F in hexadecimal. Likewise, the number 13 in decimal is represented by the symbol D in hex. So when we're done, we can say that 64801 base 10 becomes F D 2116. If we use the division method, it looks something like this. We start with that original number, 64801, and then we say 64801 divided by 16 is equal to 4050, remainder of 1. Record that number here, so 4050, and then we'll keep a running column for remainders here. 4050 divided by 16 is equal to 253 with a remainder of 2. We write that number here, 253, remainder of 2. 253 divided by 16 is 15 with a remainder of 13. 15 divided by 16 is 0 with a remainder of 15. As before, use your note card converter. 15 becomes F in hexadecimal, and 13 becomes E. When we're all done, we say 64801 base 10 is equal to F D 21 base 16. In some places, you'll see this expressed as 0x F D21, where these leading digits indicate that we're dealing with a hex number. In fact, this is pretty common when you're dealing with programming languages. We may as well continue our examples and try to work this backwards to check our work. We have the number FD21. We want to convert that into decimal. Once again, expanded form. That F becomes a 15, so that's 15 times 16 cubed, plus D, which becomes 13 by 16 squared, plus 2 by 16 plus 1 by 1. 61440 plus 3328 plus 32 plus 1 gives us our original number of 64801, base 10. One last time, let's do a hex to binary conversion. We write the hex number with a little bit of spacing between the characters. And once again, we use that 3x5 note card converter, where you find that F is 1111, D 1101, 20010, and the symbol 1 is 0001. You can see that each hex digit expands to 4 binary digits. You can see why this is the preferred form. It's much easier to communicate with another person using 4 symbols than it is to use all 16 that would have resulted from binary. As a side note, in the previous lecture we talked about gates. What I want to do now is just present the family of 2 input gates. We start out with inputs B and A, keeping in mind that we're only concerning ourselves with 2 input logic gates. Inputs B and A can take on one of 4 combinations: 0, 0, 0, 1, 1, 0, or 1, 1. If the output was 0, 0, 0, 1, we would call that an AND gate with a symbol that looks like this. Had the outputs been 0, 1, 1, 0, we would call that an exclusive OR gate with a symbol that's somewhat reminiscent of the OR gate, but it contains an extra curve at the input. So again, inputs A and B. That's the exclusive OR gate symbol. 0, 1, 1, 1 is an OR gate. We've explored that one before. Again, 2 input OR gate. The NOR gate is just the OR gate, but inverted. So 1, 0, 0, 0. So you can see anywhere that there was a 1, it becomes a 0. Anywhere there was a 0, it becomes a 1. This symbol looks like our OR gate. However, it has an inversion bubble on the output. Exclusive NOR. So now we're taking our exclusive OR and we're just inverting all of the outputs. So it's 1, 0, 0, 1. We start that symbol by drawing the exclusive OR. Then we add an inversion bubble on the output. The NAND gate is the opposite of the AND gate. That becomes 1, 1, 1, 0. That symbol looks just like the AND gate, except it has an inversion bubble on the output. As a reminder, here's how we use this chart. We have 2 inputs, B and A. For example, if we looked at the exclusive NOR, we could say input B and A. The output, which we typically describe as F, it'll take on a value of 0 if B is 0, A is 1, or the other way around, it's still 0. If both A and B are 1, then the output F will be 1. So that's just a nice way of describing all of our different 2 input gates. What I'd like to do now is focus in on this exclusive OR gate, specifically when the gate is active. So it looks like if B is 0 and A is 1, the gate will activate. So we could say that is B not A, it will also activate, which is to say F will be 1 when we have B A not. The Boolean expression for that would be F is equal to B not A or B A not. This is the sum of products form. As a challenge, let's see if we can build that exclusive OR gate using ands, ors, and nots. In fact, let's use the array style. There's input B with an inverter. So we would call this the B line, and this here is the B not line. Input A with an inverter. And now we need two AND gates. So you can see this is an AND gate here, a 2-input AND gate. This is a 2-input AND gate. In some examples, you'll see the inputs to these AND gates crossing like so. And you might be asked to program the circuit. For example, if you wanted this output, the output of this AND gate, to be B not A, you would come over here to the B not line and put a bubble there. So now you've connected B not to the upper input of this AND gate. And now you have A, which is right here. So we are programming this array. This line is B A not. So on the upper one, we find the B connection. And then we look for the not A connection. So there, we've programmed these two AND gates to be sensitive to those inputs. That takes care of that and that. What we need to do now is join them together with an OR gate. And there you have it. We have created B not A or B A not using an array style. Continuing on with our theme of circling back to problems to check our work, let's take this circuit and see if we can convert it into a truth table. It has two inputs, B and A. They can take on values 0, 0, 0, 1, 1, 0, and 1, 1. When you're going from logic gates to truth tables, it helps if you look for those intermediate wires. For example, B not A, and here's the other one, B A not. And then finally we have our output F. When we go to fill out these columns, we look at the inputs. This is the B not, and this is A. And it looks like there's only one condition where B not and A is true. So we would put a 1 here. All others would be 0. We do the same here. We're looking for B, which puts us in these two rows, and we're looking for A not, which is right there. So that becomes 0, 0, 1, 0. And now we're looking for F, and we know that F is B not A or B A not. So that's this, which ends up being 0. This would be a 1, and a 0. So it looks like we've come full circle and we've explored the exclusive OR gate in multiple different ways. Here's another circuit that we can convert to a truth table. Input C, B, and then we have A. But A goes through an inverter. The results then go through an OR gate. This has 3 inputs, so we write those in our truth table as C, B, A, starting with our A column, 0, 1, 0, 1. then 0, 1, 0, 1. The B column, 2 zeros, 2 ones, 2 zeros, 2 ones, and the C column, 1, 2, 3, 4 zeros, and then 4 ones. So with 3 inputs, there are 8 unique possibilities. The intermediate wires in this particular case are C, B, so we'll make a column for that here, and A naught. So here's our A naught column. C is true here, and B is true here. So it looks like the values are 0, 0, 0, 0, 0, 0, 1, 1. A naught would just be the inverse of this column here, so that would be 1, 0, 1, 0, 1, 0, 1, 0. Finally, we have the output, which we'll call F. That is composed of an OR operation between these two columns. That would be 1, 0, 1, 0, 1, 0, 1, 1. In our last example, we'll take a Boolean expression, in this case F is equal to D naught C A or D C B naught A naught, and convert that to a truth table. You'll see there are 4 inputs, D, C, B, and A. And now I have to be really careful to fit everything on this page. Zero, 1, 0, 1, 0, 1, 0, 1. If you recall the order of operations, you'll remember that an AND has higher precedence than OR. That means our columns are the first AND gates. So this is a 3-input AND gate, and this, DC B naught A naught, is a 4-input AND gate. And once we have those two columns, we can compute our output F. Our first term is D naught, so that's this piece here. C, that's this piece, and then we're looking for conditions where A is true. Looks like that only occurs in 2 places, so this becomes 0, 0, 0, 0, 0, 1, 0, 1. We would identify this row as D naught C B A. We would also identify this row as D naught C B naught A. In our next discussion, we'll see that this naming of rows is quite important to us. We'll also find a way of simplifying it. As for this column, we're looking for conditions where D is true, so that's here. C is true, that would be this. B naught, it's here. And finally, A naught. It looks like that only occurs in one place. So this column becomes all zeros except right here. Here's an observation that you should keep in mind. If you have 4 terms, right? If you have all of the terms for any given system, you will identify one and only one position in the truth table. Likewise, if you have only 3 terms, you will identify 2 positions in the truth table. While it's not shown in this particular diagram, if you had only 2 terms, for example, if you had D naught, C naught, you would have identified 4. If you had a single term, for example, D naught, you would have identified 8. Once again, we're getting ahead of ourselves, but that's something to keep in the back of your mind as we continue on with our next lecture. Okay, putting this all together, we are going to perform an OR operation on these last two columns. That becomes 0, 0, 0, 0, 0, 1, because of that 1 there, 0, 1, and then 0, 0, 0, 0, 1, 0, 0, 0. Without too much effort, we can convert that into a gate level circuit. Just for convenience, I'm going to record our Boolean expression here using the array style. We will need a single 3-input AND gate and a single 4-input AND gate. We'll use this as the 3-input AND gate and this as the 4-input AND gate. And of course, they are connected to an OR gate. Our terms are D naught C A, D naught C, and A. For the lower AND gate, it's D, C, B naught, and A naught. Before we finish, I wanted to leave you with a few notes. The circuits that we've explored right now are not optimized. Here the word optimized implies either simple, which means the minimum number of gates, or often it also means fast. Ideally, we want logic circuits that are very simple to construct with the fewest number of gates, and we want circuits that can operate as fast as possible. To be complete, we should also add energy efficient. And these two are often competing terms. Something that is fast is not necessarily energy efficient, and vice versa. As a parting thought, consider this. There are many different ways to construct a circuit. You could construct one circuit using things like AND gates and inverters. You could construct a functionally equivalent circuit using only, say, NAND gates. In fact, you could use nothing but NAND gates if you wanted. Either way, each of these circuits could be represented by a truth table. So let this be input C, B, A, and say output F. We would describe this as a many-to-one relationship. There are many different ways to make a circuit such that each circuit will have the same truth table. We might describe this circuit as the simple circuit. And maybe this one, which is built using entirely different components with an entirely different structure, is the fast circuit. But either way, both circuits will perform an identical, they will have the same truth table.